mode.
So just one introduction, Annie. So Annie and I go back 5-6 years when I was in a committee in the University of Antwerp to assess the feasibility of getting valorization out of mathematical methods. And since then, she has been the coordinator of an xpower.eu project in which I'm also involved. Let's say, please go ahead, Annie.
Okay, thank you, Johan, for the introduction. You can see the full screen display
yes.
of the slides. Okay, that's nice. Anyway, thanks also for inviting me to give a talk today at this interesting 2-day symposium. And the topic that you proposed was that I would speak on sparse interpolation, exponential analysis, and last but not least, superresolution. The results that I will show are joint work with my collaborator Wenxin Li from the University of Stirling in Scotland, and also joint work with a PhD student, Ferre Knapkens. Of course, I first want to tell you what sparse interpolation is and what exactly exponential analysis is. What does it cover? Before we explain how to combine these two techniques, or at least methods known from these two domains. Sparse interpolation is in computer algebra. Exponential analysis is in signal processing. So how can we combine the knowledge from these two domains into a method that delivers super resolution? And even before doing so, why would we be interested in finding such a method? So where is super resolution needed, among other things? And I will answer the last question first, and then afterwards go over the rest of the table of contents. One of the obvious application is the so-called direction of arrival estimation, where one tries to figure out the angle theta that indicates where the source is that emits a certain signal. And the receptors that you see on the x-axis, they can be antennas or they can be microphones. It can be different things. The source here, which hits these antennas under an angle theta, need not be a single source. So you can also have multiple sources. What we do assume, just for the moment, for simplicity, is that we're dealing with a fixed frequency, omega, and a constant amplitude indicated by Sj. But more complicated models are possible. But to keep it simple as a first introduction, so assume we have several of those sources with fixed frequency and amplitude, several of them hitting these antennas, then whatever is received at antenna Fk can be written down as a linear combination of exponential functions. So that's what you see here. I don't know whether you can see my mouse cursor. Johan, I don't know whether I should use another symbol for the mouse cursor.
No, we can see your mouse moving.
Okay, that's good. So you have a superposition here of sources as explained above, and we are after these theta j's because that's what you don't know. These problems arise in many circumstances. For instance, one of the more interesting ones I find that I'm working at now is one where we are following a pod of whales and we're trying to figure out from which direction their vocalizations come. A standard problem in these setups is that when you have an array of these receptors, be it antennas or hydrophones or whatever, is that they influence each other because of the electromagnetics, etc. So you should preferably not put them too close to one another. But on the other hand, physics dictate a maximum distance between two such receptors in terms of the frequency omega that is present in your signal. Of course, you want, in order to avoid this mutual influence, you want to be able to increase the distance between the receptors. And that's more or less where we would need the super resolution. If you go beyond the current physics or beyond what the current physics can allow you to do, and you still want to pick up the same information as when the receptors were closer, more closely placed, then you're dealing with a super resolution problem. On a larger scale, we have worked with the Dutch Institute for Radio Astronomy, ASTRON, and their LOFAR radio telescope configuration, which consists of several, let's say, a radio telescope antenna configuration. This one is lying on the floor, yeah, as you see in the left-hand picture, which is not your usual picture of a radio telescope, but they deal with a network of several of those across the Netherlands and a large number of other European countries. And if you want to view it even bigger, so our techniques can be used, and we are currently collaborating with this team. Our technique can be used in a square kilometer array project, which is a radio telescope project, a joint project from South Africa and Australia, with its head offices in the UK. And the plan is that they outperform the Hubble telescope by at least a factor of 50. So again, super resolution. You can, of course, interchange the role of receptor and object. Like if your object is on the ground rather than your receptors, and your measuring unit is in the air, for instance, a UAV, then you're dealing with the localization problem. The UAV emits a signal to the object, and then by some reflection, it can accurately compute your position. Again, to do that very accurately, there are physics boundaries, but we want to break those, and we were also able to do that. In radar, you have both types. You can have the radar on the ground, trying to follow a plane in the air and looking for scatterers, or you can have an object on the ground and a moving radar high up, like when you do satellite imaging. Of course, we don't need a lot of imagination to understand that all this technology can be built into our automotive radar, and other super resolution problems present themselves in industry where induction motors are, let's say, the main workhorses, and they need a lot of maintenance. And one of the things that people need to pick up are these fine peaks that I indicate here, which occur in the motor current signature analysis. And these are weak and fine signals that you need to be able to pick up well before anything goes wrong with the induction motor. At the beginning, they are less pronounced. By the time that the motor has several cracks or breaks, then they, like in the last picture, they are more prominent, but you would like to pick them up early enough, and not resort to, let's say, unnecessary replacement of parts or so, just to be ahead of these faint signals peeping up. You do want to know when it happens, and you do not want to just replace parts to prevent that because you don't have the technology to monitor it. Exponential functions deal with periodicity. Periodicity means patterns. So we also published a paper, or we obtained some results on modeling patterns in weavings, so textures. We allow to detect errors, a tear or a stain in the texture during production or afterwards. And the method works without learning. So it's not like a machine learning tool where you first need to train the machine in order to recognize or be able to classify the texture. Here, the texture is immediately modeled in this exponential expression with periodic terms. And so any aberration from there is immediately picked up. We are planning to move into natural models, and that's where we will probably again collaborate with Johan, trying to find patterns for the pictures that I show here at the bottom row. So that is, let's say, work in progress. Now that I have motivated you, let me explain what is sparse interpolation. We all know interpolation from our courses of numerical analysis. Given some data, you were supposed to come up with a simple expression, very often a polynomial, that kind of mimics the behavior of these data. And if I give you the challenge to reverse engineer the function that I show here, one coefficient plus another term of x to the power 100, then with the standard polynomial interpolation that we have all learned in our courses, we would need 101 samples to be able to find this expression, to reverse engineer it. The reason being that our methods that we were taught, they work with consecutive powers of x, and so you start with a constant and you go all the way up to x to the power 100, finding that there are 99 zero coefficients. Now, if you look at it from a different perspective, you do realize that the problem to fit data brought forth by this function only have 4 unknowns, namely 2 powers and 2 coefficients. And you could say a 5th unknown, namely, I need to know that it's 2 terms. So from 5 samples, I should be able, rather than from 101, I should be able to entirely come up with this model. I should be able to tell you it contains 2 polynomial terms, it's a constant term, it's x to the power 100, and I compute you, I give you the 2 coefficients. But in order to do that, you need different methods than the ones you know from your standard numerical analysis course. So more generally, sparse interpolation is about fitting a model to data that is sparse in a way, meaning in the model, a lot of non-zero terms are not carried. The terms are not zero. And the aim is that which of the basis functions x to the power k most properly match these data. Very often it is an inverse problem. Some physics or engineering argument has told you that there is something like a polynomial expression that fits these data, or more generally, there is something like a trigonometric polynomial that fits these data, and then you're coming closer to the signal processing problem statement. But both these problem statements, whether it be polynomial or trigonometric polynomial, are a special case of the exponential sparse interpolation. And I add one restriction. This problem statement is dealt with when you have the availability of equidistantly sampled data. So your data values Fs are collected at points in space or in time that are at equal distances. So let's say you start at 0 and then you go on, you collect data 0, delta, 2 delta, 3 delta. Very often in a time environment that is very easy. Yeah, like there's a sensor and there's a data point collected every minute or every day or whatever. Now, what were these physics restraints that I talked about when I was presenting the DOA problem? And I will just briefly touch upon that, but I will appeal to your gut feeling. Imagine you have data that come from this function, cosine 3x. And the data were collected here at the red points. So the cosine 3x function is the black function. And I collect data, I sample that function at the red dots here, the red open circles. Then I will not be able to tell you that the data come from cosine 3x because there is another periodic function that fits these data. And the reason is that in order for me to be certain that I get the correct frequency, which is this 3, the sampling step times frequency should lie within the interval minus pi pi. So in absolute value, it should be bounded above pi pi. And that is what is called the Shannon-Nyquist condition. That is the one that dictates the standard distance between these receptors when you are working in a DOA, direction of arrival context. And this is precisely what we want to break. So while the physics tells us that we would not be able to pick up this cosine 3x, we want to be able to do that because it's a higher frequency, so it's a finer resolution that we need. It's super resolution. We move into exponential analysis. It's a standard technique in digital signal processing. I don't want to go into too much detail here. Given some exponential phenomena, like a signal coming in, you want to figure out what the frequencies are, possibly including decay rates, and what the amplitudes are, possibly including a phase shift, and how many terms you need in such a model to fit the data that you have collected. So from the background literature, you know that an exponential model is suitable. Now your challenge is to figure out what are my parameters. For the exponential function, that's a parameter, that's a nonlinear parameter, and what are my linear coefficients. And that is the problem of exponential analysis. You analyze your data by an exponential model. How do you do that? You approach it as an interpolation problem. So given your data Fs, again collected at equidistant points xs, under the Nyquist constraint. For the moment we propose, I explained to you how it works under the Nyquist constraint, and then we will move into the more general. If we denote capital phi j as an abbreviate for this expression, then we see that we are facing a polynomial system, at least if my cursor wants to move on. Okay, I'll do it like that. So your data phi fs dictate a polynomial system if you want to model them by an exponential expression. Look at the coefficient matrix of this polynomial system. So the alphas are unknown and the phi's are unknown, but the coefficient matrix is a van der Monde matrix. There you have coefficients 1, 1, 1 in the first row, then capital phi 1 up to phi n, your Vandermonde nodes, and then all the consecutive powers of the elements on that row. Okay, good. I need to work a little bit differently. In order to extract these nonlinear parameters phi j, I'm going to compose Hankel matrices. A Hankel matrix has equal values on upward sloping diagonals. So if I start with FR in the corner here, the diagonal from southwest to northeast has the values FR plus 1 and FR plus 1. And that's how I go on. Because the samples come from an exponential problem statement, I can factorize this Hankel matrix in a very particular way. And here are my Vandermonde matrices again. The Hankel matrix is a product of 3. If the upper left corner element is F0, and these 3 elements are here, the coefficients alpha are on the diagonal. If I have FR as upper left element in the Hankel matrix, it factorizes into 4 matrices, the same 3 as for Hn0, and 1 diagonal matrix with the rth power of these capital phi's here. That makes life easy for me, because now if I look at this difference, this matrix pencil, Hn1 minus lambda Hn0, then I easily see that the generalized eigenvalues lambda equal the phi j's, because that's the only extra factor that appears in the Hn1. So I can get my phi information by solving a generalized eigenvalue problem. Okay, let's go down. Okay. So I have this capital phi j, the generalized eigenvalue. Now I need to extract the nonlinear parameter phi j that is inside the capital phi j. That I can only do unambiguously under the Nyquist constraint. And this is why this constraint is there. So you can compute this value, but in order to use this as a pointer to the unambiguous frequency that you're looking for, your phi j times delta should not exceed 1 period. How do I find the coefficients? Well, once these values were extracted as generalized eigenvalues, I go back to my polynomial system of interpolation conditions, and then the alphas are obtained from the Vandermonde linear system, where I plug in the phi j values that I just computed. So this is the easy part in the problem statement. How do I find n? Also there are some nice results. In order to keep within the time limit, I will cut it short here. N is actually the numerical rank, or the mathematical rank of your Hankel matrix. And you compute it usually by an SVD of the Hankel, and then what you find is a numerical rank. Can be unreliable here and there, and we also have a solution for that. So now you have seen the need for super resolution. You know what sparse interpolation is about. It's about not needing too many data to pick up information in a modeling problem. And you have seen how exponential analysis in signal processing is in a way a sparse interpolation problem. Now, what can we combine from both to move the theory further? We apply to the above a scale and shift paradigm that was also successful already in wavelet theory. What we are going to do is we are going to stretch delta and sometimes translate the samples. So stretching and translating is a typical wavelet action. And instead of sampling at multiples of delta, we choose ourselves a, let's say, dilation factor or a scale factor sigma. We will sample at multiples of sigma delta. And we could fill our Hankel matrix with FR in the upper left corner. So now we will also look at samples that we want to collect at a shift over tau delta. So on the one hand, there will be samples at 0 sigma delta, 2 sigma delta, 3 sigma delta. And on the other hand, there will be samples where this whole set is shifted over tau delta. So samples at tau delta, tau plus sigma delta, tau plus 2 sigma delta, tau plus 3 sigma delta, like that. But then if you look at the Hankel, it very much has the same structure as before. Think of the FR. I've used this letter tau now as a subscript in the upper left corner. And rather than jumping over one delta, you jump over sigma deltas every time you change the row or column. So the factorization remains very much the same, only the Vandermonde now does not start with the phi 1 up to phi n as nodes, but the sigma power of these phi 1 up to phi n. And the upper left element is on the diagonal of the fourth factor in the factorization. Generalized eigenvalue problems in the picture again. So you cannot get phi j because you have not collected at multiples of delta, but you can collect phi j to the power sigma, which may get you in problems, of course, because our Nyquist condition was satisfied for phi j and delta, not for phi j and sigma delta. So this is where, let's say, where the method actually stops unless we find a solution to the problem. Now we cannot extract the parameter phi j from this generalized eigenvalue, which we could do in the previous situation. So we need to come up with something else. What we do is we compute another power of these capital phi j's, one that will be mutually prime with capital phi j to the power sigma. And we do that from these shifted samples. Because the exponential function has a nice property, namely exponential of a sum is a product of exponentials. So you can put this shift outside, you can push it into the coefficient. So after you have the first group of phi's as generalized eigenvalues, you can get the second group of powers from coefficients. And then, oh, sorry, other direction. And then you can look at the intersection of all the candidate arguments in an interval that is now too large. Rather than being one period, you have sigma times the period or tau times the period. But since they're mutually prime, only one is in the intersection. And that is how you can break the Shannon-Nyquist rate or the Shannon-Nyquist constraint and work with samples that are located further apart. You need to combine this with some results from approximation theory and signal processing in order to come to a full algorithm. But I think time does not permit me to go into these details. So I'd rather prefer to show you two nice examples. I want to discuss the solution of a 20-term difficult exponential analysis problem that we were inspired to write up by people who work with magnetic resonance spectroscopy. So they often face signal data where some of the frequencies are very close to one another, and they need to separate them. One of the applications that we were told is, for instance, in the differential diagnosis of degenerative diseases, like you need to know whether it's one degenerative disease or the other one, and then you need to be able to separate the concentrations of two brain metabolites, and in the MRS signal, they would just lie spec one next to the other. So we constructed this 20-term problem, and as you can see, the first graph here is the standard output from the standard methods before applying super resolution. The 20 terms appear in clusters. There's about 5 clusters of different numbers of terms. Sometimes it's 3, 4, 5, 6. And if you model the data, look at the right-hand picture, and I will tell you exactly what you need to look for. The open circles is the correct solution in that display. So you got the model right if you hit the circle with the dark, with the full bullets. And you can easily see that we don't do that. It doesn't happen. Of course, the answer is not so wrong. It's not that the method entirely fails. It just cannot separate the signal. It doesn't offer super resolution. Like if you look at this first result here, there's 5 terms, 5 or 6, okay? They're all almost colliding, and the method picks up that it's probably some of them are added into one term here, and another one, a few others are added into this term. So rather than separating it into 5 or 6 terms, it thinks it's just 2 terms. And that's the same thing that happens everywhere here. Now let's look at the super resolution results. So this is when you apply the method that I just explained. By enlarging the power of that phi j, okay, I get an echo from somewhere here. Okay, by enlarging the power of that phi j, you kind of swirl your powers or your frequencies apart, because you don't go around the unit circle once, you go several times around the unit circle. And slight differences between 2 points on the unit circle grow when you take their consecutive powers. And that's what happens here. And then you see that we do indeed hit all the bullets within a very reasonable accuracy. So you've got 3 here, 4 or 5 there, etc. In another challenge, we were asked whether it would be possible that we pick up like very faint terms that one doesn't know whether they are present, yes or no. And so we came up with this illustration where we have a 3-term signal containing 2 clear exponential contributions. They're periodic, so it's the argument is an imaginary number, pure imaginary. The 3rd term is almost not visible in these top graphs. If you would zoom in, you would see that there is a very slight vibration, which you can best pick up at one of the terms, like at the dip here or the tip there. That would be that 3rd term. If we add noise to it, the noise is more pronounced than the presence of that term. So standard techniques would never pick it up. They would say these data come from a bi-exponential model, and these are the 2 terms in the bi-exponential model. But there was a satellite company, and they gave us a challenge of picking up very weak terms. So, sorry, again. And to picture just the 3rd term, it's the red wave that you see here, and the gray oscillations or disturbances are an unstructured noise put on top of that 3rd term. But with the super resolution method that we came up with, and with the proper choice of sigma and tau, not difficult to get hold of. We can indeed dig up this information. And so let's say we were able to marry sparse interpolation to exponential analysis, and that trial is doing very well. We are in a collaboration with several partners, and we've published papers in several domains, several application domains, because as we all know in this consortium, math is very basic. It can be applied at a great variety of problem statements. Thank you for attending this presentation.
Yeah, just thank you very much, Annie. So maybe just if you can show this slide, yes. So yeah.
You want the references or the?
No, just a slide of the map. So
the map, yes.
Upper right, there's Genicap. That's my company. So that's how we are involved in this as well. So yeah, we had the discussion last week or 2 weeks ago. I think it's a very powerful. I'm sure it's a very powerful method. But you look at it from a mathematical perspective. I look at it from a biological perspective. And I think in the next 10 years, an important step will be made. It could be made in joining these two methods using different basis functions and so on. So that's why I thought it was important to put you on this day together with Paolo and Pino to see where there can be overlaps. So thank you again for your nice presentation. Are there any questions from the audience? We still have a lot of time.
Yes, I'm sorry. Good morning. A little question. Hello. A little question. Congratulations for the presentation. Very interesting. And about you talk about the classification of images, for patterns, recognitions, and so on.
Yeah. So you mean the textures?
Yes. Have you, about the machine learning, used some trained or some architectures?
Yes, well, we have. In our paper, we have compared our approach to that of machine learning. So we have also used machine learning techniques, and we perform a very comparably. The advantage being that we have a very small memory footprint. You just need to build a mathematical model that represents the texture, and we can skip the learning phase.
But are you using some architectures, like, for example, convolutional architectures in deep learning, or only from a mathematical point of view? Have you trained some architectures?
Yes, we have. Yes. If you want, I can send Johan the paper on this result, and then he can forward it to you.
Yes, I will do that. Yeah.
Oh, thanks. No, because I'm studying the deep learning techniques, and just about classification of images, we used, for example, convolutional or recurrent or hybrid techniques. So I'm interested to know your techniques if you improved.
Yeah, the secret when combining machine learning and this thing is that you need to understand the power of both methods. So when you see that there's a pattern, I don't think we should resort to big cannons like machine learning, because this is easy to pick up. Your eye immediately sees that it's not difficult to recognize this pattern. You can continue to add it to the left and the bottom and the right easily. But so for these types of textures, I would never recommend machine learning. But when it's a very complicated image, then the machine learning helps you out. And that, I think that's where the power is of all these artificial intelligence tools. Some of our students now use them for the simplest job, which you should not. You should use them for very complicated jobs where we cannot come up with a simple one-line mathematical formula.
Yeah. If I can add something here.
Okay. Okay. So I'm waiting for your PDF or your paper. Thank you very much.
We'll forward it. So just adding to this, so looking at the lower range of images, so in 2012, 2013, Johan Fougerolles and his students, and also me as a co-author, published results on recognizing images. And one of the results was, for example, a very simple experiment, recognizing road signs. They can be triangular, hexagonal, or circular. And with my formula, you could pick it up immediately. So you did not have to teach a machine to learn, which is happening.
Exactly.
And that's the power of these mathematical methods. They can be very simple one-line equation and pick up things that are much simpler to do than with machine learning, which is making things more difficult.
Exactly.
But on this texture pattern, I have an absolutely great idea, Annie, and this is the following. I'm not sure if you know Arnold's cat.
I don't think I do.
Arnold's cat is something extremely interesting. It's an illustration of a theorem by Poincaré. You start with an image of a cat, and then you tear it up according to some transformations. And then after, let's say, 300 rounds, you get the cat again. Huh?
Yeah. Okay. I have come across it once.
Yeah.
Great, but go on. Yes.
Yeah, and my idea would be if we have all the intermediate stages, these 299 stages, they're all pattern-like, and maybe we can test it there. That would be a great example. Just as an example. So I will write to you on this. So
yeah, good, great. Yes, we can do that.
Then you can, if we can get back the transformations, that would even be better. Then we have a full picture because Poincaré's theorem is so important. And anyway, good.
And I had a comment.
Yes, please.
I have been very much interested in this talk. And since you have mentioned the possibility of using different exponential, I would like to mention the possibility of using a different type of trigonometric functions, which are based on generalization of the Euler formula on the basis of Euler representation. On the basis of these, the definition of this function, which are very stable, are very well known, and so on, is based on van der Monde determinant. This could be an help also in the sense that you have already a set of functions which you can use as basis for this type of expansions. If the speaker is interested, I can send the paper with it on. In this paper, there is no, of course, no numerical analysis, but I think that in principle they can be used for this type of implementation.
Yeah, I would greatly appreciate to receive that paper indeed. I was also very attentive in your talk where I picked up that some generalizations of the exponential, according to me, definitely lend themselves to this approach. So one thing that might be done is you could model population dynamics by collecting samples and then fit one of these functions to the data with the techniques that I have described here.
So
I think there's room for joint work or for future work, as you want to call it.
No, I have many experimental data on free electron laser evolution, and so a very good interpolation of the oscillating part would be very, very interesting to understand whether the model we have used is correct or not. It would be really very helpful. Thanks a lot anyway for the suggestion. I will send you our papers.
Just to be sure, Pino, Annie, Pino, you answered to Paolo in this talk of this morning, but Pino asked the question and he will give the talk this afternoon. But I also mentioned to Annie these different exponentials and complex numbers. And yeah, it was today's goal to combine things. And I think that will work nicely. So thank you very much, Annie, for your very nice presentation.